Now we're going to turn our attention to the idea of calculating an area and what's known as a Riemann sum. As usual, let's take a look at the primary objectives for these next several videos. First of all, we want to understand and use sigma notation to write an evaluated sum. So if you're not familiar with sigma notation, which you may or may not have seen in a pre-calculus or an algebra class, then we need to talk about this a little bit. We also want to understand the concept of an area. Just what does that mean? We want to approximate the area of a plane region using Riemann sums. And actually, I should probably talk a little bit about what a plane region is, because some of you may not be familiar with that term. We also want to find the area of a plane region using limits. Okay, so if you go back at what we've done, we know that a derivative results in the instantaneous rate of change in a curve. So if I take the derivative of f and I'm looking at it at a specific value, say at a, I know that the value of the derivative at a gives me the slope of the tangent line, which is the instantaneous rate of change in the function. But what does an integral give me? Okay, f prime gives me the instantaneous rate of change, but what does the antiderivative, what does the integral give me? That's something that we're going to be discussing here. That's the whole point in the next several videos. Now, also, before I go on, let's go ahead and take a moment and actually talk about what a plane region is. A plane region is simply any region on the plane, and we've been dealing with the xy plane. So if we're talking about the area of a plane region, this is the plane, and if we have some function, say from a to b, that looks like this, we start talking about the area. We're talking about the area between the curve and the x-axis on the xy plane, hence plane region. That's what that means. Okay, so what does it mean to actually find area under the curve? Well, if I come out here and say I go from 1 to 3 and maybe all the way up to 5, and I draw this rectangular region, well, I know what the area is. It's a rectangle, and the concept of area makes a lot of sense. And actually, if you take a look at this, 3 minus 1 is 2. So this has a width of 2, it has a height of 10. So the area equals 5 times 2, which is obviously 10. Now, this is a constant function. If I think of it from a to b, of a constant function, that will give me simply a rectangle. But what happens if my function is not constant? What happens if it's some type of generic function? Well, what happens if I have a function from a to b that looks like this? Now, the area under the curve, that should make sense. It'd be kind of obvious, is this. But the question is, how do I find it? How do I find that area? It's not a rectangle. I can't take some known formula, height times width, and say, there it is. It's not a triangle, so I can't take 1/2 height times base. How do I find that area? Now, this process is called integration. The process of finding that area under the curve. Now, suppose that this function that I'm working with happens to model some type of physical phenomenon, such as examples velocity. Suppose a vehicle travels at a constant speed of 25 miles per hour for 3 hours. How far has that vehicle traveled? Well, you know, if you have 25 miles per hour and you multiply it by 3 hours, well, the hour units is going to cancel. 3 times 25 equals 75, and the units are miles. You know the thing's gone 75 miles. But what if I draw this? Think of it this way. What if I draw this with the t-axis, where here's 1 hour, 2 hours, 3 hours, and then up here, this is the time axis. in hours. And up here is the velocity. And I'm at 25 miles an hour. And I stay constant at 25 miles an hour for 3 hours. Well, if I look at this box that I create and look at the area of the box, this area is 25 times 3. That area is 75. And that 75 represents the area that's under this curve. It happens to be a constant function. And the interpretation for the area in this case is actually distance traveled. So suppose velocity was non-constant. See, something like this, a fifth grader could calculate. But what if I had a function for 3 hours? 1, 2, 3 hours. Here's a time axis. And perhaps my velocity started at 0, and I accelerated up and slowed down, went constant for a while, accelerated, and then leveled off again at the very end. Again, if I can find this area is going to equal the distance traveled. Now, we've always seen this idea with indefinite integrals because we said that if s is a position function, position can be thought of as distance traveled, s prime of t equals the velocity. Well, if I integrate the velocity, I end up with the position. So that's what we're doing here. So we need a way of integration to find this area under the curve. That's what the integration is going to actually do. That amounts to, in this physical example, if I integrate this function that represents velocity, in this physical example, I end up with the total distance that's traveled. Now what we need is actually a method of calculating this area for some type of irregular shaped function. And this leads us to the whole idea of Riemann sums and the sigma notation.